Hello. Yes. Yes. You got a question? We can do that in a minute. All right. So we're reviewing binomial probabilities. I looked up Department of Education website says at least data up to 2008 was the latest they had a lot of data for, that 76% of public school teachers are female. They also had private schools listed there, and they said that was 74%. Since there's a lot fewer private schools than public schools, if you merge it all together, I bet it's still pretty close to 76. They did not merge all the data together. So then I took a sample of elementary school, or sorry, not elementary. I took a sample of public school teachers, and I got 31 teachers, and I found that 9 of them were female. Is this unusual if the average is 76%? So that's the question we're trying to answer. And most of you came up with, yes, it is unusual? Okay, so let's try and analyze why. So the first thing I would do to analyze this, I would say, well, if 76 is what expected, what would be average for a group of 31? So that means we want to calculate the mean, which is 0.76 times 31. Anybody know what that is? 23.6-ish? Yeah, so 23.6. So what that means to me is that on average, I would expect to find 23 or 24 out of 31 teachers be female. Okay, that's what I would. That's how we interpret that. So this means 23 or 24 out of 31 should be female. That's what we expect to happen on average. Bless you. That means if we had tons of samples of size 31, on average we'll find that 23 or 24 are female. That's all that means. What did we find in this sample? In this sample, we found 9 out of 31. Did anyone calculate what is 9 out of 31? Yeah. What is it? 0.00000. What is not? What's 9 divided by 31? Okay, 0.29. So it's about 29%. You're freaking me out there, Michael. Okay, it's about 29%. So I'm expecting 76%. I got 29%. That seems low to me. Okay, but is it really low? Okay, so how do we define really low? So that's when we look at tail probabilities. Okay, so 9 out of 31 seems low. How low? Okay. It was 0.00050. Okay, so here we've got some distribution. I'm just going to draw it as a smooth curve, even though it's not. The mean of my curve should be about 23, 24-ish. Let's call it 23.6. 31 is the edge of this distribution. I found a number way over here that's 9. So to determine if 9 is too low, I need to examine what is the probability that x is less than or equal to 9. I need to look at this whole tail. Because you have to look at tails because the bigger the sample size, an individual measurement in that sample is insignificant. You got to look at a bunch of them. All right, so let's see. In that calculation, is that a binomial CDF or PDF? PDF, okay. And so on, I think, let's see, on the TI, we would do binom CDF, and they would want to know, let's see, what's the order again? It's it's NPX, right? And on Excel, it's binom dist, is that right? Dot dist, binom dot dist. On other spreadsheets, I don't think they have the dot, like Google spreadsheets or OpenOffice or Numbers. I think they lack the dot. And there, I think it's XNP. I think it's XNP, right? Yeah, XNP. So slightly different notation in Excel than on the TI. Oh, and then you have to state whether it's cumulative or not. So we want a cumulative, so the last thing would be a true. If we wanted the single probability, it would be a false. No, I got to do 9 or less. Here's the deal, right? Let me show you another picture. I actually drew this distribution. Here's the distribution. Let's make it even bigger. and change the scale a wee bit. Okay, so here's the distribution. The problem is, if there actually is stuff going on in this tail over here, we're just not seeing it. The larger the sample size, the probability of any individual thing happening is low because they all have to share one. And so in general, just looking at a single number to determine if something's unusual is worthless, because then everything's going to be unusual if you have a large sample size. So we always look at the tail for unusually low or unusually high. That's just the rule, because otherwise you get no information, nothing helpful. So you got to use tails. So here's my particular distribution here. Can anyone see what the highest stack is? 24. Does 24 sound familiar? Yeah, if we round it to the nearest whole number, that's the mean, right? And that's always going to happen on a binomial distribution. If you round to the mean to a whole number, that will be the highest stack. And so we're looking at 9, and I can't even see the height of the 9 stack, right? It's wicked small, right? Can I, oops, I didn't grab the right spot. Oh, well. Anyway, that's that distribution. So I'm trying to calculate this tail over here. Oh, gosh. All right, technical problems. And so you entered, so again, we got to have the CDF, not the PDF here. We want the whole tail. And what do we get for a value if we calculate that tail? So we're going to do binom CDF 31, 0.76, comma 9, which is this probability, to 3 decimal places. It's 0. Yeah, it's about 0. If we went to 4 decimal places, 5 decimal places, I think, really? Oh, shit. Oh, okay, let me double check, just because I thought it was bigger than that, but I could be wrong. So second variables, I think it's option B that I want. Oh, what did I hit? Wrong button. Let's just scroll down. Okay. So I'm going to type, what, 31 trials? P is 0.76. And X is, oh yeah, oops. Oh, 5's close to 6. Okay. And I get, so yeah, I get I get 7 decimal places and then a 4 shows up. So let's check it on a spreadsheet. Where's Excel when you want it? There it is. So in Excel, we want the cumulative to be true. Did you put true in the last column? Okay. Well, I just did. Oh, you added them up. Okay. Now, in general, if we were talking about like n was 300 and I was looking like 250 and higher, I wouldn't want to do that. But even if you do them individually, it should still add up. So we're going to do binom dist tab s is equal to 9, comma 31 trials, comma probability of success is 0.76, and cumulative is true. I want the whole tail. Close, and Excel says same number. Yeah, 0.70 and then 449 is what Excel says. So it agrees. Let's blow this view up in case we come back to it. Zoom 200. There we go. Okay. So the tail probability is wicked small. So does that mean 9 out of 31 is unusual? Yeah. So what? So how would I tell my mother that? I would say something like this: finding 9 out of 31 teachers are female is an extremely low number of what? Female teachers. It's not the probability we're describing here, it's the particular number that we found, which is 9. 9 is wicked low. Too low if we expect 76%. So it's an extremely low number of female teachers out of 31. Why again was it low? Well, I was expecting 76%. Okay. Now, am I guaranteed 76%? No, I'm not. Okay, so a couple things could be true here. Well, I have a weird random sample. Or maybe my sample isn't that random. Hey, Gary, how did you come up with these 31 teachers? Oh, I went to the Pendleton School District website and looked up the middle school. The middle school has 31 teachers, 9 are female. Is that a random sample? No, there is nothing random about that sample. Could be a reason. I don't know. Pendleton, Rodeo Land, you got more guys hanging out than girls. I don't know. Maybe there's some bias in the school district towards men at a higher level, middle school versus elementary school. Guess where I got the 12? A local elementary school. All the teachers were female. There were 12 of them. Yeah. Yeah. I did a little elementary school and I was the only guy. I taught middle school once and half the staff was female, half the staff was male. High school, more males than females. It does seem that it goes up, but I haven't seen that data. Okay. I don't know why. To look into that, but maybe. I had no desire to coach. I didn't last long. I coach math. Oh yeah, that's right. Yeah. Okay. So yes. So it's not. It's when we're talking about something being unusually low or unusually high. Although probability is part of that decision, it's the particular number that we found. In this case, the number of women out of whatever. Okay. So let's look at the other one. The other one said case 2 was there were 12 teachers and all 12 of them were female. We're still expecting the national average, 76%. So if I just double check, what is 76% of 12? It's about 9, isn't it? .1-ish. Yeah. Okay, so we're just going to call it 9. So it's about 9. Is 12 higher than 9? Yes. Okay, so 12 is higher than 9, so 12 is greater than 9. So the next question, is 12 unusually high if we were expecting 9? So is 12 unusually high? And the conditions there are if 76% is expected. And what does expected mean? Expected is a mean. It's the national average here. Okay. Distribution. I graphed this one too. And let's get it up. That's this one right there. I can blow that up a little more. Oops. All right, so there's that distribution. Get over here, would you? Okay. So let's see. Now I'm doing unusually high, so that means I want a right tail. So in this case, I want to know what is the probability of having 12 or more. But wait, there's only 12. So in this case, the right tail only has a single number in it. Sometimes there's more than one number. It just depends. So there's 2 ways I can calculate this. So I want to know what is the probability that x is greater than or equal to 12. Now, in this case, and this will not always be the case, that happens to be equal to the probability that x is exactly 12, because n and x are the same number. If this was like n was 50 and x was 47, I'd have more probabilities in the tail to consider. Okay. So I'm really still going to consider this a CDF. It's a cumulative distribution. Okay, I'm only accumulating one thing, but in general, there's more than one. Now, here's the problem with the cumulative distribution function in Excel and on the TIs. It only does left tails. What am I doing here? I'm doing a right tail. So then we have to just figure out how to do a right tail. So that's a rough estimate of my distribution. There's my 9. Here's my 12. I need that tail right there. So I need to go 1 minus the left tail. What number ends my left tail here? 11, right? So that means I want to calculate 1 minus the probability that x is less than or equal to 11. So that, again, would be 1 minus the binom CDF or binom dist. And in this case, x is, let's see, I gotta remember which is which. Ti is npx, right? So that'd be 12, 0.76, comma 11. So let's calculate that. I'm going to do it in Excel just to be different. Equals 1 minus the binom dist. Number of trials in this case is 11 in the left tail. Number of trials is 12. Probability is 0.76. And this is true cumulative. Oh shit, why do I keep doing that? Weird. I guess so. It's like, yeah, it's 3/4, right? It's okay. So I get about 3.7%. Is that what you guys got? Unless I made a mistake. Now that happens to be the same. That should be the same result as just the probability of 12. So I'm just going to double check that by doing just a binomial PDF. So find the binomial on your calculator. Find the binomial PDF for just 12. That should be the same number. So equals binom dist. Oh shit, wrong button. Try it again. Tab, there we go. Number of trials is 12. 12, 0.76. And let's see, this is not cumulative, so I want false here. I'm in Excel. And whew, I got the same number. It's good. Do you guys understand why I got the same number? Because the tail just happened to be a single number. So I could use the PDF function instead of the CDF. All right, so let's call that what? 3.7%? Sure, my mother would like that number. So this tail is about 3.7%. What's our cutoff most of the time for a low probability? 5%? Yeah, so that right there is less than 5%. So what's our conclusion? About 12 out of 12 female teachers. It is an unusually high number of female teachers when we're expecting 76%. And you all wrote a sentence that sounds something like that? Okay, so I'm just going to put my sentence down, then we get to do normal stuff. So 12 out of 12 females is an unusually high number of females since we were expecting about 9. Why were we expecting about 9 again? That was 76% of 12, yeah. We were and there's a million different sentences one could write. Oops, I guess I should put female in there. Okay, so I'm just trying to, from past experience, the idea of what does it mean to be an unusually high number of observations versus what is an unusually low number of observations is a tough concept to grasp, so I just wanted to make sure we're getting that down. Feeling a little better about it? Or you already had it maybe? Getting there?
So we got 5% rule, so would that be right on the test?
Yeah. Good question. The range rule of thumb. I'm so glad you asked about that. Let's do the range rule of thumb too. Okay, range rule of thumb. What the hell is that? Thumb, I think they spelled that right. Range rule of thumb says that if you look 2 standard deviations below the mean and 2 standard deviations above the mean, you would expect to find what percent of the data? Almost 95, yeah, 95% of data. expected. Yes, 3 standard deviations is 99.7. Now this comes from what rule? The range rule of thumb we derived from another rule. The empirical rule. Okay, and what's the empirical rule relate to? What kind of probability distribution? Any probability distribution? Normal distribution, uniform distribution, binomial distribution, Poisson distribution? Normal. Yeah, not all bells are normal, but yeah, normal distribution. If distribution is normal. So sometimes we apply the range rule of thumb when we shouldn't. If the data is too skewed one way or another, the range rule of thumb might not apply very well. But it's a relatively easy calculation. Okay. So let's see, what's the standard deviation here? Standard deviation is square root of NPQ. So N is 12, P is 0.76. That means Q is what, 0.24? 24 hundredths? Anyone whip out that number on a calculator? To 1 decimal place? 2.4? Anyone else get that? Confirmation? Okay, so that means I want to take my mean. What was my mean about here? We're calling about 9. So I want to, from 9, I want to take 2.4 away twice. What do we get when we do that? The mean is about 9. We calculated that earlier. So it's 9 minus 2.4 minus 2.4 again. I think it's like 5.2-ish. You didn't get 2.4? Well, what did you get? 1.4? Okay, let's check. Okay, more people agree on 1.4, Jeremy. Clear. Square root, there we go, of 12 times 0.76, and then 1. Oh, you're doing 31? Okay, that'll change it. Yeah, I'm just going to do the 12 one since we were on that one, 24. Okay, 1.5. That makes it nice, because if we double 1.5, we get 3. 9 minus 3 is 6 on the low end. And on the high end, 9 plus 3 is 12. So what that means is if this is, if I can apply the empirical rule, then I would expect 95% of my data to be between 6 and 12 females out of 12. Sometimes. The question is that inclusive? Yeah, I would consider it inclusive. We got some rounding problems there, and we also have a small sample size, so it's kind of questionable. Now, the other thing is my data actually normal? Let's take a look. Normal means it's a bell shape and it's symmetric about the middle. Well, the middle number between 0 and 12 is 5.5. So here's x equals, no, that's not right. It's 5.5, right? What's 12 divided by, no, wait a minute. It's somewhere in the middle. Well, what's right in between 0 and 12? It's not 6, it would be 5.5, I'm pretty sure. Or is it, yeah? Yes, 13 divided by 2. That's 6.5. Okay, yeah. All right. X equals, okay, I'm having a mental breakdown. Let's see. If I was going between 1 and 12, I would be at 6, but I'm including 0 in this too. So that drags it down a little bit. No, I was right the first time. X equals 5.5. Yeah. So that's the middle between 0 and 12. Is my distribution symmetrically coming down from each side of that? No, yeah, this isn't normally distributed. It's skewed to the left. That's where the tail is. Let's see. What numbers are two standard deviations on each side? Well, we discovered 9 and 12 are. Okay, so I just want to check something. So I want to show you a cute trick in Excel. The TI does this, but not as well. I'm going to put the numbers 0 through 12 here. I'm going to have Excel make that distribution of numbers, which I think Jeremy was probably playing around with earlier. Yeah. And then here, I'm going to calculate the binomial probabilities for each of these numbers. There's my X, my N is 12, my P is 0.76, and I want the individual probabilities for each number, so I want to go false on cumulative. And if I fill that down, those are all the individual probabilities there. Now, what I want to know is two standard deviations is what? From 6 to 12, is that right? So that means I want to sum the probabilities from 6 to 12. So if I do that here, that'll give me the probability that a number is inclusive from 6 to 12. Okay, so the probability that the number of females is 6, 7, 8, 9, 10, or 12 is 98.869%. So if it was normally distributed, what would I expect to find within two standard deviations? 95. Here I'm finding it's 98.9-ish. Is that close to 95? Not really. Not really. Does it look bell-shaped around the middle between 0 and 12? No, it does not. Yeah, not around the middle. Yeah, so sometimes you can use the normal distribution to approximate binomial ideas, and sometimes you can't. In this case, we're pushing it just a little bit. Not a lot. We can still get away with it. So if I rounded my percentage to the nearest whole number back here, wouldn't I have called it 4%? Okay, 4% is kind of close to 5. What if my rule for unusual events was 3% or 2%? Would this be an unusual event? No. Think about another thing. If you use the range rule of thumb and you put 95% in the middle, which is what the range rule of thumb does, what percent is in each tail? 2.5%. When we do our unusual event rule, what percent are we putting in the tail? 5%. So there's slightly different standards. I mentioned this before. Is there a set standard for determining what's unusual? No, it depends on the circumstances. If it's normally distributed, or so a binomial is almost normal if the percentage is near 50%. 76 isn't close enough to 50 to be normal enough, it turns out. Yeah, and we're going to play with that idea more in a couple of chapters. All right. Whew, I think we beat this one to death. If P is exactly 0.5, then a binomial is pretty darn close to normal.